Hello everyone and welcome back to a NPTEL course in Herbal Product Development and Regulatory Science. In the previous session, we saw different conventional formulations for herbal preparations. The formulations for herbal preparations are often required to ensure good palatability and stability. Now, as we consume herbal preparations, we come across few limitations of this herbal preparation as well. So, if you're talking about conventional herbal preparations, definitely they are more palatable, more stable as compared to native herbs. But when they are compared to allopathic medication, still there's a lot of scope for improvement. And as a result, from this session onwards, we move to the slightly novel drug delivery system for herbal preparation. So for this session, we will be studying a category of novel formulations, and that is liposomes. Now when we see our traditional herbal formulations, we see that when we consume herbal formulations, they are very susceptible, especially some phytoconstituents are susceptible to gastrointestinal pH. In some cases, they are not bioavailable. In some cases, their solubility may be an issue as well as absorption. So novel drug delivery system in form of liposomes takes care of all these limitations and addresses the issue. So what exactly are liposomes? When one says liposomes, the word lipo means something lipophilic and zomes means body, like your cytosomes. So liposomes are lipophilic bodies that are used to deliver drugs, and in our cases they will be delivering herbal drugs and phytoconstituents. So let's study them in details. So what are basically liposomes? Liposomes consist of layer, especially bilayer to be more specific, and these bilayers are made up of components which are called as phospholipids. In your biochemistry, we have come across different phospholipids that are present in our body, and these phospholipids are essential part of our cell membrane. Now try mimicking the very same phospholipid bilayer membrane and we come across this liposomes. So liposomes are basically vesicles which are made up of bilayer. Now whenever it is a monolayer, we call it as micelles. Whenever it is a bilayer, we call it as liposomes. So what is the little difference? Let's understand the chemistry behind it. So whenever we talk about phospholipids, we know phospholipids consist of something like a sphingolipids or glycerolipids, wherein you have a little glycerol like moiety. This is your glycerol like moiety, that is triol made up of propane, and to this glycerol moiety are attached fatty acids. Now it may have like one fatty acid. This is the second fatty acid. In this second fatty acid, let's say it's hetero. That means both fatty acids are not the same. Heterogeneous means one can be C16, other can be C18. One can be saturated, the other one can be unsaturated. So hetero means they are basically not same. So this glycerol is linked by ester linkages to two fatty acids, in this case like I said hetero fatty acids, one saturated and one unsaturated. Now when we go to the third hydroxy, the third hydroxy of it is actually attached to a phosphate group, and that phosphate moiety renders it a little bit polar, whereas your phospholipids, when I am talking about the lipid chain, they are plainly hydrocarbons. So think about hydrocarbons. The hydrocarbons are very lipid soluble and they are called as lipophilic substances, and that's the lipophilic end. When we talk about phosphate, phosphate is oxygenated. It also has the hydroxys which are attached to glycerol, and that contributes to what is called as the polar head. Now this phospholipids behave like a surfactants, wherein you have a polar head and a non-polar tail. Now if you see carefully, many such surfactants or many such phospholipid molecules come together in our body to form what is called as your bilayer membrane. So, these are the phospholipid heads and these are the tails. So, this forms what are called as the bilayer membrane, and your cell wall is precisely made out of it. Now, imagine a scenario where it starts taking a curve and gradually forms a circular what is called as a vesicle. Remember, if it is a single layer, I am just drawing it here, it is called as micelle. If it is a bilayer, it is called as vesicle. Now, the advantage of vesicle is, if you see vesicle, this inside of this vesicle are all polar heads. Now, if you see this sandwich layer, they consist of non-polar lipids, and again outside they are polar heads. So, you have two polar regions and a sandwiched non-polar region. So, this microscopic bilayered vesicles in case of liposomes may range anywhere between 30 nanometers to several hundred micrometers, even like 1000 micrometers in size, but more the size, the greater, there is a lot of instability to it. So, this may be what you call it as single concentric vesicle, or they may have one inside the other, like this multiple, even hundreds of concentric bilayers of phospholipids. So, they are multilamellar, they are called as. Now, what happens here is, how is this a drug delivery system? Now, if you see this, you can imagine this to be something like your laddu, wherein the inside is a full cavity, and this motichur laddu's cavity contains a very what you call it as polar moieties. Now, inside this polar moieties, because of the polarity, the solvent which generally stays in very comfortably is water. So, I am just putting here water, and because water stays here inside this vesicle very comfortably, most of the water soluble drugs will start residing inside this cavity. So, inside this cavity, like your, imagine you have your laddu or your Ferrero Rocher chocolate, where you have this inner layer, and this inner layer is filled up of water, and it contains all your water soluble drugs. Now, you just move little bit outside, you go to a very lipophilic region, and this lipophilic region represents that fatty acids. Now, this hydrocarbons of fatty acids are extensively lipophilic, and as a result lipophilic drugs will stay here. Not only will lipophilic drugs stay here, even some traces of lipophilic solvents which solubilize this drug would prefer to stay in this region. Now, moving further out, again this is a polar moiety. So, this vesicle can nicely be suspended in aqueous media. So, we can suspend liposomes in water, they will be very stable because the exterior is made up of polar heads, a little interior is made up of lipophilic moieties which can support or solubilize your lipophilic drug, and the interior the cavity of the liposome again contains an aqueous layer. So, it can support both the aqueous, that is water soluble drugs, as well as lipid soluble drug, and that is where it is more advantageous. The added advantage is it always mimics your body because it is made up of a phospholipid like your cell membrane, and as a result the absorption and assimilation of liposomes happens much more conveniently as compared to your other dosage forms. So, you can classify the liposomes generally based on their size. If you have to classify them based on the size somewhere between 30 to 100 nanometer range is generally referred to as small unilamellar vesicles. Now, unilamellar means just a single bilayer. Now, if you go to little bigger size, greater than 100 nanometers, you can call them as large unilamellar vesicles, and sometimes you can have something like your GUVs also. So, here Depending again upon your vesicle size, you can have multiples, but like I said, the more the size increases beyond 1000 micrometers or so, that might lead to instability. In some cases, there is rearrangement being formed, and then instead of a single or a unilamellar vesicle, you come across what is called as multilamellar. Now, what does multilamellar means? Imagine putting this inside this. So, you have lamellae inside lamellae, and that's precisely what is called as multilamellar vesicle. So, as the size increases, there is good chance the other lamellae will fit inside the aqueous region because of its stability in aqueous media, as we saw previously, and you can come across what are called as multilamellar vesicles. And again, if the size goes greater, you have multivesicular vesicles. So, multiples or compounded form of that. You can also classify your liposomes depending upon its applications. Now, basically, you generally take the membrane as a phospholipid membrane, and that's what precisely when we say conventional liposomes, they are made up of basically of phosphatidylcholine, serine or conventional phospholipids. Now, in some cases, a little advancement in technology has given rise to what are called as altered or more specific liposomes, which can help us in targeting. Now, this depending upon the what exactly we need out of this liposomes, you can create what are called as stimulus responsive. This stimulus may be something like a pH stimuli, wherein you can use dioligo, something like a phosphatidyl ethanol amine derivative, which is sensitive to pH. You can use different polymers of different phosphatidyl derivatives which are sensitive to temperature and other conditions including osmomolarity, salt concentration and so on. So, depending upon when you say your stomach pH or your cancer cell pH, or if there is any temperature variation between the tissues and you want to selectively deliver your liposomes there, what will happen is at lower temperature it won't release the drug, but when the temperature is conducive or slightly elevated as compared to that of body, your liposomes will freely release the drug. Then you have stealth. Now, what happens with liposomes is because body treats phospholipids as its own, it gets absorbed and assimilated very easily. But then it takes or makes it part of the body, and as a result, it can kind of metabolize and body can eventually take care of it. In some cases, we want our liposomes to go undetected by the body. A very stealth technology like you use in aircraft, you can also use stealth technology in cases of liposomes. So, we need to coat it with some polymer which will go undetected by the body. So, otherwise the phospholipids, it will just treat it as its own and it will show the same processes. So, most of the times we do something called as polyethylene glycol or pegylation. Now, pegylation prevents your RES system from detecting it, and as a result they remain stealth, they remain undetected, and their life in our body increases as compared to the conventional ones. You can also modify them by adding certain what are called as specific proteins or enzymes, wherein when they come in contact with those proteins or binding sites, only then the liposome can release the drugs. So, you can stick certain ligands to it where they can attach in a way very similar to your ELISA. You can attach something like antibodies over it. You can attach something like specific sugars over it to which it can bind and then target your drug in there. Not only that, your liposomes also nowadays contain certain agents like your fluorescence agents, your radio contrast agents, as well as something as simple as your magnetic particles, which can help not only in therapy but also diagnosis of certain disease condition. Such cases or such type of liposomes are called as theranostic liposomes. Now let's go a little bit deep into the components of liposomes. What are this made up of? So by nature, when I say liposomes, what comes to your mind is phospholipids. So generally glycerophospholipids, as we saw, or sphingomyelins naturally are used for preparation of your liposomes. So this can be coming from the sources such as your soy, like your soy lecithin, sunflower oil, like your sunflower lecithin, or from egg, like your egg lecithin. In some cases, rather than using crude lecithins, even purified compounds such as phosphatidylcholine, which is majoritarily used up to, if not 100% pure, like 70% pure phosphatidylcholine, 80% pure phosphatidylcholine is used. Phosphatidylserine, phosphatidylethanolamine, phosphatidylinositol, even many other natural phosphatidyl derivatives are used. Even synthetic phosphatidyl derivatives such as dialkyl or trialkyl lipids. The common example is dipalmitoyl phosphatidylcholine can be used. Now apart from this, the properties of the liposomes, especially the surface properties of liposomes, we saw can be modified, but that is more stabilized when you add compounds such as sterols. So if you see in terms of sterol, the most abundantly used sterols as far as liposomes are concerned is cholesterol. It is cheap, it is easily available, somewhere in the ratio 1:1, 1:2 when compared to your phospholipids, and it is seen that it fits in very properly. So if you see your steroids contain like 4-ring structure. And the 5th ring is 5-member. The remaining all rings are your 6-membered ring and might contain certain aliphatic group. So this all acts as a very lipophilic moiety, but if you see something like your cholesterol, it also has an hydroxy. So this goes and sits in the polar part, this goes and fits in the non-polar part. So they form an integral part of your liposome and as a result modulate your membrane permeability, fluidity, as well as they make your phospholipid layer very stable, which would otherwise easily be destabilized by charged ions. Not only that, in terms of specificity, even your cationic liposomes have been prepared. So if you go to see stability, that can be enhanced by addition of sterols, and this include your cholesterol or plant-based sterols such as your beta-sitosterol. Now in addition to that, for preparation especially, that is formation of your vesicles, is further enhanced by addition of surfactants that act as stabilizing agents and later on can be removed by osmosis or any other methods. So for size reduction, rapid emulsification, permeation, as well as for stabilization, you might add surfactants such as sodium cholate, spans, especially span 80, span 60, or your twins such as twin 60, twin 80 might be added. In some cases they are retained up to certain concentration, in some cases they are kind of removed by using what is called as your osmotic membrane or dialysis membrane. Now we just saw specific cases. Whenever you have specific application, you can functionalize or add functional groups to this phospholipid bilayer. This can be your PEG for your stealth technology, antibodies, proteins which can be used for specific ligand targeting. Anionic and cationic agents can be added for binding. In fact, cationic agents are added when you are supposed to carry something like a genetic material, DNA, RNA, and certain viral proteins and so on. The reason being most of them are negatively charged. So if you add a positively charged functionalization to your phospholipids, they are stabilized and chances of their denaturation or elimination from the vesicle is very low. In some cases, like I said, when you want temperature stimuli or temperature based release, you can have something like a synthetic phosphatidylcholine also mixed in, which is like your 1,2-dipalmitoyl glycerophosphatidylcholine. So that's very sensitive, a little elevated temperature as compared to body, and it will release your drug very comfortably. Now once you have the components, let's see how they are prepared. The preparation methods are enormous, but we'll just discuss a few methods owing to limited time that we can give to this topic. So I'll just discuss the major methods which are used. The first one is what is called as thin film hydration. In this, what is done is your drug is taken here. So especially your lipid and fat soluble or oleaginous drug is taken here. Something like your curcumin, which is very lipid soluble, is taken, and it is dissolved in organic solvent. So you have your lipids, phosphatidylcholine, you have your curcumin, dissolve it in organic solvent and then evaporate. Now as you evaporate this, the organic solvent like your chloroform or dichloromethane will evaporate and it will form a thin layer. Now once this thin layer or a phospholipid membrane is formed over your glassware, especially a round bottom flask, what you can do is add your buffer or an aqueous solution that you want to prepare it, and then stir it or shake it vigorously. When you stir it or shake it vigorously, this phospholipid membrane which is formed along with the drug dislodges and forms vesicles depending upon the concentration. Now this gives rise to what is called as a liposomal formulation based on thin film hydration. Another method is what we call it as reverse phase evaporation. Now in the reverse phase evaporation, what is done is lipids are dissolved in an organic solvent. Again, you can think about curcumin, surfactant, and well as your phospholipids. All of them are dissolved in an organic solvent mixed with a aqueous layer. Now in this case, your aqueous layer may contain something like a very polar drugs. The advantage of liposome is you can have both the loadings. So mix it with something like a polar drug, take for example tannins, which are very water soluble. Now slowly under stirring, you will start evaporating the organic solvent. So what happens is the lipid soluble drug like curcumin remain in the lipid layer, the organic solvent is evaporating, and as a result this lipid start precipitating, and as it starts precipitating, it starts developing micelle like structure as it is contracting in nature, and when completely your organic solvent evaporates under reduced pressure, you get thin film or powdery film of your liposomal particles inside the water. Now the next method is ethanol injection. In some cases it is ethanol, some people also use ethers for preparation. So ethanol injection, also ether injection can work with it. Again you take your drug, your lipid soluble material, dissolve it in a suitable solvent, and that solvent you slowly with the help of syringe inject it into a very high speed stirring assembly which contains water as well as your water soluble drug. Now this contains your aqueous solution and your alcohol you are injecting it. What happens in the process is your ethanol, specifically in this case when you are talking about a ethanol injection, ethanol and water are very miscible. So your ethanol and water mixes together but your lipid doesn't. So in that case it starts forming micelles, and you can see that over a period of time as you heat and the ethanol is evaporated, you can gradually get your micelles. Again there is something called as dehydration rehydration method. So in this case first the lipids are hydrated, and they are hydrated by using a very low concentration of lipid which are dispersed in water. So allow them to hydrate properly in water. Lipids won't clearly dissolve in water, so you might require a help of sonicator. So sonicate it possible, and then you will get a dispersion as they break because of sonication. So this dispersion of lipids which is actually prepared under sonication is flushed with nitrogen and completely kind of dehydrated. In some cases strong vacuum is applied to dehydrate it. Now when this happens during the dehydration process, they tend to form your vesicles, and these vesicles are later on to this when you add water, that is your rehydration step. So during this step, that is your rehydration step, they form what are called as large vesicles encapsulating your drug moieties. Now in addition to that, two modern day techniques are also used, and that is your supercritical fluidic method and microfluidic method. So what is done is, if you see your supercritical fluidic method, this method uses something like a supercritical carbon dioxide. Now supercritical carbon dioxide is carbon dioxide which exhibits both, that is the liquid and gaseous property, and has a good affinity for lipophilic compounds. So your lipophilic drugs, your lipophilic polymers, it will all dissolve well, and then this solution is slowly pumped into a supercritical chamber which has your drug in the aqueous phase. So when I am pumping supercritical carbon dioxide in a drug based chamber containing your drug in an aqueous layer, what is going to happen is, it's going to mix uniformly, and slowly when you decompress, the supercritical carbon dioxide is going to go off in the same way like your solvent evaporation, and as it is going off, it will precipitate out the lipids, and these lipids often tend to form liposomes. So you can create a very high pressured system like your HPLC pump. You can use your supercritical chamber, and then with the help of this pump and supercritical chamber, you can create your liposomes therein. Nowadays, you also have what are called as microfluidic devices. So this microfluidic devices, from one side you can put the aqueous layer, from the other side you can put in the organic layer, and then allow them to mix over a period of time, and as they are traveling, they will mix to each other. There will be certain heat and agitation involved, and then when they are kind of counteracting each other, because of the alcohol as well as water is miscible, you will see your drug encapsulated in a lipid bilayer. Not only that, like I said, there are many other methods. Some of them involve your French press or high pressure preparation of your liposomes. Other ways are also there. So these are just few methods which can be used for preparation of liposomes. Now once you prepare liposomes, many of them are at a bigger size. If you want to create particles which are really smaller size, which are much more stable, you need to further fine tune it or size reduce it. So size reduction of liposomes can be done with the help of sonication. The more you sonicate it at a little higher frequency, this vesicles break into still finer vesicles. Or extrusion, like a French press extruder, where you have certain membranes with a defined pore size, and when you apply a very high pressure to your liposomes, they are forced to extrude through this, and as they are extruding through this, they reduce in their particle size. Then again you have high pressure homogenization, which works somewhere at about 150 to even 900 megapascal. So that's a lot of pressure, and that pressure creates rupturing of these vesicles into tiny particles and so on. Alternatively, you can also convert it into a freeze thaw cycles, where you can freeze your liposomes at minus 100 plus degrees Celsius and again thaw it to room temperature. This repeated cycles of freeze thaw are also known to decrease the particle size. Now once you have prepared it, it's very important to see to ensure that you have really made liposomes or not. The first important parameter is particle size and shape. That can be done with the help of a technique called as dynamic light scattering. So when you are talking about tiny particles, when light falls on it, they will scatter the light. Some of will reflect, some of will diffract, and this light scattering gives us an idea about the gap between two particles. And if you see very fine particles, they have in themselves what is called as the Brownian motion. So they keep on oscillating in the Brownian movement. So your dynamic light scattering is a technique which is tuned to capture the Brownian motion, and based on that it can detect the size, shape as well as charge. But if you want to specifically see it, you can use what is called as scanning electron microscope. So it's an electron microscope which can kind of pick up a very nano size particles also based on the electron beam falling on the particles. So scanning electron deflects and you can see back, whereas transmission electrons you have to fracture the particle and how it passes. So you can say if it is passing here, it's more transparent. If this is bilayer, this is more opaque. So here the transmission will be comparatively less. So how transparent, translucent it is, or in some case you go to what is called as cryo-TEM, so that the surface remains somewhere as below as -180 degrees Celsius, so that there is no change in the structure. The structure remains rigid, and that's how you can assess it. At the same time, sometimes you can just put it on a mica layer and then use something called as a probe tip, and that is what is called as an atomic force microscopy. This probe tip will release electrons, and this electrons will detect like every nanometer of your particle and compare it, analyze it. So your particle shape, size can be analyzed by dynamic light scattering, microscopes such as, or microscopic technologies such as SEM, TEM, cryo-TEM which is frozen, as well as electron based what is called as a TIP, atomic force microscopy. Now in terms of charge, you have to see that the particles need to be charged, otherwise they will coalesce if they are very neutral. But imagine this is like -30 and this is -30, there is a good chance they will repel each other. So you see the charge, especially the zeta potential on this. So zeta potential or surface charge can again be measured with help of dynamic light scattering, because this charge also decides the Brownian movement, as well as depending upon the size. So electrophoretic mobility is basically when you have a charge electrode, and how much your particles travel towards the electrode will depend on the charge. So you can measure the charge based on the mobility, you can measure the charge based on dynamic light scattering. You can see the lamellarity. Lamellarity is how many lamellas are there. So this how you can analyze, like I said, cryo-TEM, where you have frozen it at -180 plus, it's not going to move, and then you see how much transmission happens like this. So whenever there's a layer, your electrons will move more freely. Whenever there's phospholipid bilayer which is more viscous, here you will have more opacities. So you will get a good idea about it. We also know that our phospholipid contains phosphate. So if you are radio labeling it by P31 isomer, you can again detect it by radioactivity based on a X-ray analysis. Now you can also check the phase behavior based on X-ray diffraction. Again, what you call it as a transition temperature, especially for lipids or phospholipids, based on differential scanning, colorimetry or thermogravimetric analysis. This will give you interactions, associations as well as stability, especially the temperature stability. The most important parameter is how much drug it is able to hold. This can be done or studied by quality control test, which is called as encapsulation efficiency. So in this case, the vesicles, especially the liposomes, are taken, they are centrifuged. Then post that they are subjected to dialysis, wherein other surfactants and other metabolites are removed, wherein your phospholipids stay inside, and then you can determine using HPLC or any other chromatographic methods how much of the content was actually there and how much is bound. So you can see the bound content, you can see the unbound content, you can see the release as well as the supernatant when you do the analysis, especially the dialysis followed by centrifugation. So what are the advantages and limitations of liposomes? So when you prepare liposomes, we saw that they are convenient, but the techniques of polymers might be little expensive and the process is little tedious. So let's compare the pros and cons of liposomes as compared to your conventional preparation. So in terms of the pros or the advantages, you can see that as compared to the conventional formulations, this definitely are more bioavailable because they are made up of phospholipids. Now if you see carefully, when you talk about syrups, we said that yes, syrups can have only water soluble or very polar drugs, but here there is a place for lipophilic drug. Here in this vesicle there is a place for hydrophilic drug as well. So it acts as a carrier for both hydrophilic as well as hydrophobic drug. It enhances stability, protects it from heat, light, oxidation to certain extent. When you kind of develop a coating, it provides a targeted drug delivery, reduces toxicity because the dose is reduced now, and being phospholipid, it is completely biocompatible and biodegradable. But when you see in terms of cons, definitely there are a lot of production costs as compared to your simple tablets capsules. This is little expensive. There is a lot of instability because if you see phospholipids, they are not stable. You cannot just boil them at 150 200 degrees Celsius, they might be unstable. Then in that case, they might lead to aggregation, leakage if the zeta potential and the vesicles are not being made properly. And if you see, many a times their circulation in body is very short because the phospholipids are used by the body. And the next thing is in terms of the technique, the scaling up, especially to a large scale, becomes a problem. So in terms of application, despite all this, there are many applications you can come across in market. Good example is, here are few, your lipo-GC, which is your Garcinia cambogia, which contains Garcinia extract up to 60%. Then you have your lipo-CoQ, which contains your enzyme CoQ up to 30%. You can have your iron supplements, Effie-leaf, which contains liposomal metal, which can also be used for diagnostic, as well as curry leaf extract. You can have kava kava, which acts as a stimulant up to 10%. And then you have also your liposomal silymarin, hepatoprotective, liposomal curcumin with black pepper and ashwagandha for immunity support, as well as plain ashwagandha containing, or regulated KSM 66 ashwagandha, and the liposomal form again for adaptogenic activities. Now here are few references if you want to know more about liposomes, and thank you everyone for your patient listening.